So my name is Michael St Clair. I am the Director of Platform Engineering at PDQ. We are in the IT space and we do device management. We just barely launched a new product that does cloud-based device management, and we actually built this in Elixir, and we utilize WebSockets to connect all of our devices to our backend server. We have a really awesome Elixir team. They're all watching remotely. Unfortunately, they couldn't make it out with us, with me. But it's really fun because we just, I got to help them recently with load testing this, and it was really kind of crazy to me how efficient Elixir was scaling to hundreds of thousands of WebSocket all concurrent connections. So personally, I've been working with Elixir since 2016 when my team started rewriting a PHP app into Elixir. And kind of ever since then, I've just really loved Elixir, and it's been my go-to project for just about everything I do. Up until last year, I was usually doing like a React front end to pair with an Elixir backend, but I started diving into LiveView this year, and I've just absolutely just loved how easy it is. And so we all have at least one side project. I have 3. If you want any more details, they're all on my GitHub. The first 2 are open source, so a lot of code to look through there. But today I'm actually going to be talking about the last one, which is QueryDesk, and that is the database GUI and proxy that I built with Elixir. So before we talk about how I built it, I want to give a little context on why I built it. This is kind of a question everybody's been giving me as I've told them what my talk is today. So in every engineering position I've been in, engineers usually need access to the production database, usually to debug issues around bad data, and then often to follow up with updating that data that's in a bad state because of a bug. Every company I've been in has implemented this access in a little bit different way. Some will just issue read-only credentials and let engineers share and connect directly to the database to query it. Some will build tools similar to QueryDesk. And usually in most startups, everybody just has full production access. Why not, right? I'm sure we've all dealt with some fun outage where somebody accidentally dropped a table or maybe the entire database. So that's exactly why I built QueryDesk. Is it gives a really nice auditable view that lets engineers connect and log queries to an individual engineer to see what they are accessing. And then if you need to update it, an engineer can submit a query for review, and once it's approved, then they can run it. So it kind of solves all those needs of being able to read and then also fix data. However, my favorite part is actually the data protection feature that I was able to build in. So anytime you submit a query, if you have data protection on, it will analyze the query and determine if you are selecting any sensitive fields. So these are usually when you're dealing with HIPAA data or like privacy laws, you'll need to be able to handle that kind of data protection. So it will detect those fields if they're in your query, and then it actually rewrites it before it gets submitted to the database. And that way, the sensitive data never actually leaves your database. Okay. So next, a little bit about how QueryDesk is architected. So it's an Elixir app on the back end with a LiveView front end, and that is the server side. And it is, so Phoenix and LiveView, but then it also utilizes Ecto for a lot of the GUI pieces. Ecto has adapters for Postgres, MySQL, and SQL Server, so I'm easily able to connect into all of those. And using dynamic supervisors and, with Ecto, I can connect to all of those depending on the different configurations that you provide. There is also an optional agent component that is also written in Elixir and connects back to the server over a WebSocket. However, this uses a custom serializer with protobuf messages. As we'll get into later, the Postgres protocol will talk over a binary message. And so the JSON serializer that comes by default with WebSockets was not going to work. Let's see. Okay. So before we dive into the proxy side of things, I'm going to give a quick demo on the LiveView GUI app. And let me switch to this screen. OK, so this is the LiveView QueryDesk app. And it might look familiar as your typical database client has your tables on the left side, and then your data is shown. So This is just running an Ecto query that takes a table name as a variable. And what Ecto makes it really nice is then I can add things like sorting. And you just click on the field using Phoenix Click, and then you can handle it, and it will return the data sorted. I also use, so if anybody was here in the previous talk, as Chris Nelson was talking about, is using JavaScript inside of your LiveView. So if you'll notice, the timestamps here are actually formatted to the browser time zone and also have a relative time added to them. This is all processed with a web component. I also like lit, as Chris was mentioning. And so this passes the date time that comes back as UTC to Luxon, and then Luxon is able to parse that and then output the value here. I also have just a custom query view. This uses CodeMirror, also is wrapped inside of a custom element. And this allows me to use the Phoenix custom hooks to listen for when the query changes inside of here. So then I can pass that to LiveView to run that query when this button is pressed. You can select multiple users. So in this case, there's a read-only user that doesn't require any reviews to run the query. And then there's a query desk user that has full access, and that requires one review. So if you want to update it, you would have to use that other user. So if you run the query, it will give you the data back similar to the table view. And then if you were to try to use the user that required a review, it's going to change to a button that says request a review. And then you would come over to the queries view, and as soon as you have your approvals, you'll be able to run that query. I believe, let me change back to slides. Okay, so as I was working on building the GUI, I realized it was going to take quite a bit to get to a full feature set. There's a lot of things that go into building a database client. And even then, if I had full features, us developers are stubborn. We have our tools we like to use, and we don't want to change off of them. So that is where I started looking into building a proxy with Elixir. And that would let me allow users to use whatever database they wanted, and then that could connect through to Postgres. Yes. So let's talk about how to actually build a Postgres proxy. So to do this, I've kind of split it up into 3 sections. First, we're going to talk about what binaries actually look like in Elixir. And this will be really critical because the Postgres protocol actually uses binaries to communicate. So to really explain that, it'll be easier to start with knowing what binaries look like in Elixir, just in case anyone's not familiar already. And then we'll talk about what the Postgres connection flow looks like, and then how to implement that in Elixir. So binaries, taken from the Elixir laying website, are a sequence of bytes. So they are, all binaries are also bit strings. However, the way I like to think about this is bit strings will deal at the bit level, where binaries deal at the byte level, as a binary is a bit string with bits divisible by 8. Hence the byte. Also, a fun little fact is all strings in Elixir are binaries. They are UTF-8 encoded binaries, and Elixir will detect when a binary is UTF-8 encoded and display it as a string instead of the binary. So link here, so Elixir laying the getting started guide on binaries if you did want to get any more information on those pieces. So a little bit more about binaries. So there's 256 combinations of 8 bits. Those are displayed as 0 to 255, and they are called code points. So in Elixir, if you wanted to get the code point for a character, you'd put a question mark in front of it, and that would return the relevant code point for it. So in this case, a lowercase h is represented as 104 in a code point binary. So the other thing I'll point out is all 3 of these binaries at the bottom are exactly equivalent. And if you were to type any of them into IEX, they will all output the bottom piece. If you did want to get what the binary representation of a string is, you could put it inside of the binary syntax and add a 0 null byte at the end, and the Elixir would then output the binary representation instead, if you're ever curious to see what it looks like. Okay, so let's talk about what the Postgres flow actually looks like. So when a client connects to Postgres, it is going to connect with a regular TCP connection, unencrypted, and it is going to ask Postgres whether or not it supports SSL. That message is going to look like this. So it will start with a 32-bit integer, which is the size of the message. So in this case, an SSL request message is always going to be 8 bytes. So it's always going to be 0008. And then it will have two 16-bit integers to represent what the SSL code is. And that's 1, 2, 3, 4, 5, 6, 7, 9. And this exact message is what you will see when the client is requesting SSL from Postgres. Next, SSL, Postgres is going to receive that message, and then it's going to send back whether or not it does support it. And that is a much simpler message. It's either going to be a capital S byte or a capital N byte, with S meaning that SSL is supported. From there, if assuming it does support SSL, it's immediately going to kick off an SSL handshake. And then as soon as the client receives the S byte, it will then also start the SSL handshake on its side as well. However, for the purpose of the talk, we are not going to dive into what that whole flow looks like. But I will show later how you would do that in Elixir. Once the handshake is established and we are in an encrypted connection, the client is going to send a startup message. And this startup message is going to contain details such as the user that you want to connect as, and like what database you want to connect to, what encoding, and then also whatever optional metadata. For example, one of them is application name. This headphone keeps coming on. Sorry about that. Okay, so the startup message is going to look like this. So in this case, size is going to be dynamic based off what other values you add into this. Then the next 4 bytes are going to indicate what protocol we are using. So the first 2 bytes are going to be the major version, and the second 2 bytes are going to be the minor version. So in this case, we're using 3.0. And then you're going to have a connect params binary that's embedded in this. And so connect params is going to be a repeating pattern of key value pairs, each terminated with a 0 to tell that that piece has ended. And that can repeat as many times as is needed. So an example of this would be application name is the key, then query.proxy is the value, and then the bottom piece is what that binary would look like, and that would be embedded in a bigger message. Okay, so once Postgres gets back that startup message, it is going to look at the user you're trying to authenticate with and determine what authentication method you need to use. And it is going to send back to the client that message detailing the requirements. And so now with all messages going forward, it is going to start with a letter byte that will indicate what type of message it is. So SSL request and startup are the 2 exceptions and do not start with that byte. You have to look at the other pieces of information to determine if it is that kind of message. But going forward, we can look at now the capital R, the letter. So in this case, with an auth request, it is the capital R byte. There is the size of the message. And then for a clear text password, it is going to be the integer 3. Another example is if you are doing an MD5 hashed password. And so it's going to be the same capital R byte with the size. However, in this case, it's going to be the integer 5 to tell us that we're using MD5 as the method. It will also come with an additional 4 bytes for the salt that you'd pass into your hashing function. Okay, so the client will get this, and then it will respond with the password in the appropriate encoding. And that's going to be a lowercase p message. And then in the case of MD5, the digest will be prefixed with MD5 to pass it through. Okay, so now the client has authenticated Postgres. Postgres is going to say, okay, I'm ready to accept queries. And now we all know way more about Postgres protocol than we ever wanted to, probably. So I know I was, when I finally understood this, I was very done with it. So let's talk about how we'd actually build this in Elixir now. So apparently I've learned from the last 2 talks that you can include a lot more code on slides, so I apologize. This is very abbreviated, but readable. First thing we're going to do, so remember we're accepting a non-encrypted connection to begin with. So we will use gentcp.listen. And so that's going to open a socket on that port. And you can keep looping over that port to pick up different connections using accept. And that will return the actual connection that you can talk to the databases through, talk to the clients through. So we're going to begin with gentcp.receive until we have upgraded to the SSL connection. And from there, we will use ssl.receive. So the Elixir Lang website has a really great guide on this, on specifically using task supervisors with gentcp to accept connections. And so if you wanted to build something like this, I would highly recommend starting there. My proxy is actually based on, that code looks exactly the same. So, okay, so now we have the connection from a client. And we are going to expect to receive that SSL request message. So we are going to have a basically just pattern match directly on that message and wait for that. And when we get that, we will immediately send back that we do support encryption. So we'll send back that capital S byte and immediately start a handshake. And so with this, Erlang provides a really easy method to do this, just ssl.handshake. Okay. So once that handshake is complete, we are going to receive the startup message and store the params in the state of this connection so that when we then request the password, we can link to that previous information. And in this case, we're not going to actually get a password. We're going to use a token as we are authenticating the user to the proxy, not to a database. We don't want the user to ever know what the database password is. So they will be authenticating with a token that's issued specifically to their user. So we will do the ssl.send with the capital R message saying we are requesting authentication. When we get the password message back, we will use Phoenix token verify to make sure they are authorized, and we will check that the database that they requested in the startup message is valid. And if it is, we will start that connection. So now we'll leave that client connection off to the side. It is all established, and now we're going to start our connection from the proxy to the database. So we'll use gentcp.connect. Again, it starts as an unencrypted connection. We will then send a SSL request message to the database and wait to hear back and get that capital S byte. And then we will call ssl.connect. So the thing to call out, if you remember, we used ssl.handshake on the receiving side. However, when we are the sender and upgrading the connection to SSL, we will use ssl.connect with Erlang. Why they don't operate the same, I spent hours on trying to figure out how to make that work. So, okay. So now we will go ahead and finish our setup. So we will send a startup message from our proxy to the database. And this is going to be the actual credentials for the database. These are stored encrypted inside of QueryDesk. And so the user doesn't know them, so we have to store them and then send them on to the database. We'll handle the auth. And then once we get the ready message back from Postgres, we can pass that on through to the client. Okay, so now we will be waiting to get a query message. So in this case, a query message is going to be the capital Q byte, a size, and then the query that you want to run. A lot of binaries will end with a 0 to indicate that the string is over, and so that's what you'll see here with that 0. When we pattern match on this message, we can then handle logging, do the data protection I talked about, and then we can even modify this message and send a different message to the database than the client sent to us. So that's where we'll do that. Is we'll look at that query, see if it needs to be modified, and then pass it on. Okay, so what's next for QueryDesk? I am apparently insane, so I am now also looking into building a MySQL proxy, which I think the protocol is even worse, unfortunately. I am also going to be improving the GUI and adding things like filtering and editing in the browser, and then potentially looking into adding a desktop app so it can connect to local databases as well. And then finish a Terraform plugin. One thing I guess I forgot to call out earlier is I actually use Ash on the back end as well to manage all of the like boilerplate database schema and APIs. And it made it really easy to do the initial pass on the Terraform plugin. I think it was like 20 lines to add a GraphQL API with Ash. So I highly recommend that for anybody to look at. Yeah. And that is all I have. So I'll open up for questions.